Hello everyone. In this lecture, I will talk about stability for a second type partitioning problem. And this is joint work with my supervisor, Professor Chao Xiang. And in this lecture, we will separate 4 parts. The first part, I will introduce 2 types of partitioning problems. And the second part, I will introduce type 1 hybrid surface. And here, type 1 hybrid surface means a free boundary constant mean culture hybrid surface, and rewrite FBCMC for short. And the third part, I will give the definition of type 2 hybrid surface and introduce our middle resource. And the last part, I will give our proofs, basically ideas. And now let's recall the classical parametric inequality. Let omega be a compact domain in Euclidean space with smooth boundary omega. Then we have the following inequality, and the equality holds if and only if omega is a ball. And here, the normal of omega means the volume of omega, and the volume of boundary omega means the area of boundary omega. And this theorems is equal to this theorem. Let omega in Euclidean space be a compact domain with the same volume as a ball, then the ball is error minimizing. Now we consider 2 types of partition problems. Let B in Euclidean space be a convex domain, and we look at hybrid surface in this domain, which divides B into 2 disjoint domains, B1 and B2 in different manners. And in this slides, we consider type 1 and type 2 partition problem. And here, type 1 partitioning problem means find the error minimizing hybrid surface among all hybrid surfaces in a domain B with volume fixed. And type 2 partition problem means find the error minimizing hybrid surface among all such hybrid surface in a domain B with Whiting boundary error fixed. And here, the Whiting boundary means the hybrid surface boundary lying on boundary B, and the word Whiting comes from the physical model of capillary surface. Now we give some notations. Here, mu means the unit normal vector field along X, and N bar means the unit outward normal to boundary B in B, and mu means the unit outward conormal to boundary M in M, and mu bar means the unit normal to boundary M in boundary B. And the above problems has been intensively studied by Brago and Macia in 1969 when B is a ball. And they use spherical similarization to show that total geodesic and ball and all sphere caps intersecting unit sphere consequently are unique solution for type 1 partition problem. And total geodesic and ball are unique solutions for type 2 partition problem. And later on, Benkovsky and Spanner and Amagen also study these problems independently and give the same results as Brago and Macia when B is a ball. And in fact, we can think of these problems as constructed variational problems. That is, we can minimize the error functional and the volume or Whiting error fixed. And it well known that the global mean matter must be local mean matter. Local mean matter means stable. So from the Brago and Macia results, we can imply the total geodesic n-ball and all sphere caps intersecting the unit sphere consequently are stable type 1 hybrid surface in a ball, and the total geodesic n-ball are stable type 2 hybrid surface in a ball. And we are interested to the inverse problems. That is the question 1, whether any stable type 1 hypersurface in a ball is free boundary, total geodesic and ball, and free boundary 3 caps. Question 2, whether any stable type 2 hypersurface in unit ball is total geodesic and ball. And question 3, how to measure the stability of type 2 hypersurface in general convex domain, and what's the Morse index of type 2 hypersurface. And here, the Morse index means the number of the perturbation directions which strictly decrease area out to the second order. So if the Morse index equals 0, means M is stable. And the question 1 and question 2's answer is yes. Now we give some definition. An admissible variation of X means the X is isometric immersion such that the interior M to interior B and the boundary M into boundary B. Admissible variation vector field Y defined to partial X over partial T, and from the condition, this we can imply that the Y belong to the tangent part of boundary B. And we can define the area functional in this way, AT, and the volume functional in this way, VT, and the wetting area functional, AWT. And now we can calculate the first variation formula of AT, VT, and AWT in 1, 2, 3. And here, dA and ds are the air element of M and boundary M, respectively. Now we introduce type 1 hypersurface. That means free boundary, constant mean curvature hypersurface. An emergent X from M to B is called free boundary CMC hypersurface if it is critical point of the area functional for any volume preserving variation of X. That is FBCMC equal to H equals constant, and the angle is a right angle. Of FBCMC hypersurface is called stable if the second variation of the area functional at this hypersurface is non-active among volume fixed. It's well known that the stable local minimizer free boundary CMC hypersurface are smooth locally minimizer for type 1 partition problem. And here is the precious definition of stable type 1 hypersurface. And we remark for each smooth function phi on M with the integration of phi over M equals 0, then there exists an admissible volume preserving variation of X with a variation vector field having phi mu as its normal path. This by Rose and Suamo in 1997. Now we compare the closed surface with FB CMC surface. Here are some many similar results between the closed surface in open space and FB CMC surface in a ball. Now we look at the closed surface. Hove proves that two-dimensional CMC surface in R3 of topological sphere must be round sphere. Alexanov proves that any embedded CMC surface, hypersurface in Euclidean space must be round sphere. And Barbosa Docamo proves that any stable CMC surface, hypersurface in Euclidean space must be round sphere. And we note that Huang proves that there exists CMC emerged hypersurface in R4. This is not round sphere. And Winter proves that there exists CMC emerged surface in R3, which is not round sphere. So the topological embedded stable, this condition cannot be removed. Now we look at the FBCMT surface. Known as proof that two-dimensional FBCMT surface of disk type in unit ball is spherical cap and total geodesic disk. And Rosuamo proves that embedded FBCMT hypersurface satisfying the boundary sigma belong to the half unit sphere must be a spherical cap or total geodesic disk. And here is the open questions by Rose, Vigast, and Stenberg and Zambra. The free boundary total geodesic N ball and the free boundary spherical caps are only stable at BCMC hypersurface in a ball. And this result has been proved by Rose and Vigast in special case when H equals to 0 means the minimal hypersurface. And Nunes proves the two-dimensional case. And some partial results by Rose, Suamo, Manovo, Li Xiong, Barbosa. And very recently, Wang Xia proved any dimension case. And more generally, they also gave a complete classification for stable capillary hypersurface in a ball. And here, the capillary hypersurface means the hypersurface is CMC hypersurface, and the boundary intersecting the unit sphere at a constant angle. Now we introduce type 2 hypersurface. An emergent X from M to B is called type 2 hypersurface if it is critical point of the error function for weighting error fixed. That is, type 2 hypersurface means M is minimal and the contact angle is constant. A type 2 hypersurface is called stable if the second variation of the error functional is non-negative among any weighting error preserving variations. And it's very obviously that stable type 2 hypersurface are smooth local minimizer for type 2 partition problem. And here is the precious definition of stable type 2 hypersurface. We also remark that for any smooth function phi on M with the integration of phi over boundary M equals 0, then there exists an admissible weighting array preserving variation of X with a variation vector field having phi mu as its normal part. Now we introduce our middle results. We firstly give the complete classification for type 2 stable hypersurface in a ball. Here theorem 1. A type 2 stable stationary emerged hypersurface in a n+1 ball in space forms must be total geodesic N ball. For general convex body in three-dimensional manifolds, we have theorem 2 that X be a type 2 stable stationary compact emerged surface and assume the section curvature of ME bar is non-negative and the second front form of boundary B is non-negative, and assume boundary M is embedded in boundary B. Then G plus R over 2 is smaller than 4 if G is even, and G plus R over 2 is smaller than 5 if G is odd. And here, G is a genus of M, and R is the number of the boundary component of M. And theorem's basic idea is the two cancel of balancing arguments, similar to the Rose-Vigast and Nunes, and plus the Gauss-Split formula, because we assume the boundary M is embedded in boundary B, so we can use the Gauss-Split formula in boundary B. In particular, if the angle is a right angle, we have theorem 3. Let X be a type 2 stable surface with free boundary, and assume the Ricci curvature of ME bar is non-negative, and the second form of boundary B is non-negative, then we have the following three cases. And when the last cases happens, only when H equals 0 along boundary M, and the Scott curvature of amoeba minus the Ricci curvature of amoeba equals 0 along M. Now we introduce the Merce index of M. Merce index M defined as a maximal definition of a subspace of F, here F4, on which Q restrict F is negative definite. So we have the theorem 4. We give the Merce index estimate lower bound for type 2 stationary surface. Let X be a type 2 surface, and the light amoeba is isometrically embedded in RD. Here is Euclidean space. Assume for any non-zero vector field cosine on M satisfy this strictly equality. Then we have this lower bound. We have the Merce index of M, the lower bound. Here, the RE bar denotes the Scott curvature of amoeba, and the H power boundary B denotes the mean curvature of boundary B in amoeba, and the Roma 2 denotes the second final form of embedding amoeba in RD, R power D. And we give 2 examples. The first example, let B be a mean convex domain in Euclidean space, and X be a type 2 emerged surface. Then we have the Merce index of M, the lower bound. Here the G is the genus of M, and R is the number of the boundary components of M. And the second example is let B be a mean convex domain in unit sphere, and X be a type 2 surface. Then we have the lower bound, the Merce index lower bound. And for the higher dimensional cases, we have theorem 5. Let X be a type 2 hypersurface. Let amoeba be isometrically embedded in Euclidean space. Higher dimensional Euclidean space assume for any non-zero vector field cosine on M satisfy these 2 long strictly inequality. Now, then we have the Merce index lower bound, and here the H1M boundary M R denotes the first relative homological group with the real coefficients. And we also have 2 examples. When B is a mean convex domain in Euclidean space, and when B is a mean convex domain in a unit sphere. And we remark the definition of the first homological group can be explicitly calculated in terms of homological group of M and boundary M respectively.